let's do another example. This time I want to prove that PRP security implies key recovery security. So let's just sort of get ourselves centered here. So what's the point is to show that if you have a block cipher, or more generally a function family that is secure in the sense of being a good pseudorandom permutation, then it already must be hard to recover the key if you secretly key the block cipher. And I was saying in class that somehow the PRP notion was the master notion for block cipher. This was really the gold standard. And if you could prove that your block cipher construction has good PRP security, then it already has essentially every other kind of security. So that's a little bit strong, but it implies all sorts of other kinds of properties that you might ask for from a block cipher. For example, that it's hard to recover the key. So this is the informal claim that we want to prove. As we did in the previous video, to argue this, that PRP security implies key recovery security, that means then that to break the PRP security of a block cipher, it suffices to recover the key. And this is already intuitively pretty obvious, right? If you could recover the key, then, well, we know if you can recover the key, you can do anything, right? All bets are off. So this implication is intuitively obvious, and so we're just going to prove that this is the case and see, in fact, what is the tightness of the security bound. Is it the case that PRP security tightly implies key recovery security, or is there some kind of a loss? So this is basically the way we go about proving it. So then that means our goal, if we're going to want to show that it suffices to break the key recovery security, to break the PRP security, our goal is going to be, as before, to show that if we're given access to an efficient adversary A that does in fact break the key recovery security of the block cipher, then we can construct from that an adversary B that breaks the PRP security of the block cipher with similar efficiency, and hopefully without too much loss of the key recovery strength of this adversary A. So to remind you, let's just make everything concrete. So let's fix K and N to be integers greater than 0. These are going to be respectively the key length and the block length of our block cipher E. Here is the key recovery experiment written down for you as a reminder. So key is picked, the adversary is run. Since we know there's only one kind of oracle that's at play in the key recovery experiment, and that oracle is in particular this guy here, the block cipher oracle, then we're just going to call it the block cipher oracle and not bother using the sort of generic script O that we have been using. So the adversary gets the block cipher with a secret key, and after it runs, potentially flipping some coins, it outputs its guess at the key, and it wins if it guesses correctly. And the advantage is defined to be just the probability that it does in fact guess correctly this key. The PRP experiment you know well, so I won't bother going through that again. And so our goal is going to be to show that if you give me an adversary A that's good at this game over here, then I can build an adversary B that's good at this game over here. This will suffice to prove what we want to prove. So let's go back to drawing our picture. So here is our picture drawn, and so here's our adversary A that's good supposedly at the key recovery game, which means that A is expecting to be given access to an oracle for E sub K, which again I've drawn in a dotted box because it isn't really here, but it's there to remind you that that's what this key recovery attack adversary is expecting to have in its experiment. It's going to run, it's going to ask some queries of its expected oracle, and at the end of its execution, it's going to output a guess at the key. We're trying to build an adversary B for the PRP experiment. We know that adversary B then gets one oracle, which, because we don't know whether it's E sub K or the random permutation pi, we just denote generically as the script O. We know if the bit in the PRP experiment is 1, it's E sub K. If the bit in the PRP experiment is 0, it's random permutation pi. And so we know our PRP adversary at the end of its execution has to output a bit B prime. So then what we need to do, of course, is figure out how it is that when A asks its queries, we're going to handle them. and what we're going to do with A's guess at the key after it halts. So before looking over here at the code, let's just sort of think through the intuition for this adversary we're going to build. So the intuition is, okay, let's think about this for a second. Remember, the job of the adversary that we're constructing, the one for the PRP experiment, is to try to simulate as faithfully as possible the expected environment of the key recovery adversary A. Well, he is looking for an E sub k oracle, right? If you give him one of these perfectly, then apparently it does a good job of guessing what the key is. In other words, this k prime is very often going to be the k that's up here. Well, we notice straight away that when Scripto, the PRP oracle, is in fact E sub k, in other words, when the bit is 1, then we can give a good simulation, right? And a good key recovery adversary A should give us the key. Why is it a good simulation? Because if the bit in this experiment, in the PRP experiment, is 1, then in fact our oracle is E sub k. So we can just take A's queries and pass them directly to the oracle, and then return the values back, and we'll have a perfect simulation of the oracle that A expects. So in that situation, A should give us the key fairly often. And so that's point 1 here. Point 2, let's say that we do actually have in our PRP game this as the oracle, and so we perfectly simulate the experiment that A expects. Well, what could we do with this key? Right? We have to figure out how to turn this key into a bit. Well, I think I even raised this question in class at one point, and the intuition is kind of obvious that if you have the key, let's say the k prime is k, and the oracle is in fact E sub k, right? So A has given us the correct key for our oracle. We actually can check whether or not this key is correct locally. So B, remember, adversaries always know the algorithms, they just don't know the key, right? So that means that B can compute it can compute E under this key guess for any value that it wants, right? So to make things concrete, think of E as being like AES. So it can compute AES under key K prime on any value or values that it likes. So it can check, right? If B picks an appropriate value, which we'll talk about in a second, picks an appropriate value to check under this key K prime, and then compares that result to having asked that same value, so now skipping A and asking that value directly to its oracle. If those two values match, then it's probably a good guess that the key that A gave to B is the right key. Yeah? It's certainly a right key, but it might be the correct key. So we know that if everything lines up nicely and we get this as our oracle in the PRP experiment, then we not only have a way to simulate properly the environment that our key recovery adversary expects, we also have a way to check whether or not the key recovery adversary gives us the correct key, and then turn that into a bit. Well, so I guess we should be careful, because all I've said so far is that the intuition is if we get this, then we can translate this good key guess into a good guess at the bit. By the way, I mean, if this test I just described, where you check locally some value under the block cipher keyed with K prime, if you check that against the oracle and it matches, then we should probably output 1, right? Because we know that this guy is good at recovering the key if we give it E sub k as an oracle. But what do we do in the cases, the other half of the time, 50% of the time, that the oracle is a random permutation? Well, there's no key to guess, right? So A is going to run. Of course, it doesn't know that it's been handed a random permutation oracle instead of an E sub k oracle. So it's going to run, it's going to execute its instructions, and at the end, it's going to output a guess at some key, right? Output some k-bit string. And our test, which we're proposing as a way to check this key is good, we want to be able to argue that that test is very unlikely to have us output a 1, right? So that's the intuition for point 3, is that when we have a random permutation, it should be, in fact, really unlikely that this K prime that's being handed to us by the key recovery adversary, when we encipher X under K prime, it should be really unlikely that this equals what the oracle outputs, because in this case, the oracle is a random permutation. And because random permutations, by definition, are sampled uniformly from the set of all permutations, it should be really unlikely that the mapping described by the random permutation matches the mapping described by E under key K prime for a particular point X that we'll choose. And in fact, if you like, you can pause the video here and see if you can quickly scratch out what is the probability that E sub K prime of X equals the output of a random permutation pi on X. Might even be worth trying because we're going to have to do that ultimately anyway. All right, so let's take this picture and the intuition we've just developed and turn this in now to some adversarial code. So here's our code. As usual, we write this out as an adversary B. It's a PRP adversary, so we give it this generic oracle theta. And the basic template for describing looks quite similar as in the last proof. We're going to run A. We're going to say what we do when A asks queries, and we're going to say what we do when A halts. We just do one bit of setup. So in the previous proof, we didn't do any setup. This is a little bit of setup that we'll do before B runs, and we'll see why we do this. But basically, we're initializing this set Q to the empty set. Q is going to track the queries that A asks, and we'll see why that's important. So we have this little bit of setup, and then we run A. Now, whenever A asks a query X, what we decided a moment ago was that if, in fact, our bit was 1, then we could perfectly simulate the oracle that's expected by simply sending the queries up. So we just take whatever this value is here and we pass it up to that line. So when A asks an X, we simply take the X and pass it up to the oracle, which ends up here, which responds with some value Y, which is either E sub K of X or pi of X. And we take that resulting value and we just return it back. Yeah. So this is our simulation. Whenever A asks a query X, we simply send the query X to our oracle and return the resulting value to Y. And then we add the value X that was queried by A to this query set. Right. So A asks all of its queries, and at the end it outputs some guess K prime. When A halts with its output K prime, here's what we're going to do. We want a way to check this value, right? Now, it wouldn't make any sense to check the goodness of this key on a value that was already asked to this oracle. There are two reasons for that. One is the obvious reason that if we've asked a query, we already know what the response from this oracle is going to be. And in fact, there's no probability left to speak of when we talk about the probability that this oracle outputs any particular value on X, because X has already been asked. So we want some fresh point so we can reason about the probability of Y being returned. That's reason one. Reason two is that, remember, B is a PRP adversary, and our convention is that adversaries never ask pointless queries. And in fact, to repeat a query in the PRP experiment to your oracle would be pointless because you know exactly what the value is. So B is just flat out not going to ask repeat queries. So we're going to avoid asking repeat queries when we do our check. So when A halts with its output guess K prime, we're going to pick any point Z that's in the domain. So we know that our oracle takes an n-bit string. Any point that's an n-bit string, but isn't one of the ones that was asked already, right? So some fresh point. It'll take a little bit. We'll have to have some data structure, to keep these points to make sampling of a fresh Z time efficient. That'll come out of the time complexity of B. But you can already probably think about ways that you can store these queries. For example, you might store this set in a sorted order, perhaps like in a binary tree, so you can efficiently search for whether or not a given string that you'd like to use for Z is in fact already a member of the set. You can do other things too. You can use Bloom filters or any fast data structure that allows for fast set membership tests will suffice here. In any case, we pick some fresh point z, and we check it, right? Locally, we compute e sub k prime, or this is the key that A guessed, of this fresh point z, and we check whether or not it equals the output of the oracle. And our intuition is if this oracle is e sub k, and this is a good key guess, then this ought to return true, or 1. If this is a random permutation, then the probability that a random permutation on a never-before queried point outputs this value, whatever it happens to be, should be small. All right. If that's not clear, rewind the video and go through this again. If it is clear, let's go ahead and get on with the analysis. So this is always the process, right? You draw yourself the picture, you work out your intuition for what your oracles provide to you, you write down the code for the adversary you want to build, and the next step is the analysis. So here's the analysis. I've written out a bunch of it already to sort of save time. So as before, we just write down the definition. We're trying to write the PRP advantage of this constructed adversary B. We ultimately want to write this in terms of the key recovery advantage that A gets. So by definition, this is just this statement here. And to remind you, we just reorder things. So we divide both sides by 2 and add 1/2 to both sides to separate out this probability to really highlight the fact that this is the thing we want to focus on, right? If we can express this thing as a function of the key recovery advantage of A, then we also have an expression for the PRP advantage in terms of the key recovery advantage. So we're going to focus on this. All right, so what we observed in the previous part of this slide was that when B's oracle is e sub k, then the B that we've constructed perfectly simulates the key recovery experiment for A. I say from A's perspective. Why do I say from A's perspective? Well, because I want you to be clear on the fact that if we look at the key recovery experiment here and the adversary B that we've constructed, in the key recovery experiment, what happens? The key is picked uniformly at random. Likewise, in the PRP experiment, the key is picked. This permutation is picked, but from the perspective of A, it hasn't started to run yet, right? So none of this actually matters from A's perspective. Oh, I see I have a typo here in my drawing. This shouldn't be A here. This is adversary B that we're talking about. Let's quickly fix that. Good. So, so from A's perspective, by the time it runs, if the bit in this experiment, which is B's experiment, if this bit is 1, then the oracle is e sub k, which is exactly this, right? So B's simulation, under condition on the fact that this bit is 1 of A's expected oracle environment, is perfect. Now, we're not perfectly simulating the entire experiment. Why is that? Because, well, after B runs, this is what should happen. Of course, this doesn't actually happen. What actually happens after A runs is what we define for B. But from A's perspective, from the attacker's perspective, the simulation of the expected oracle and the stuff that sets up that oracle is all perfect. So this is why I say that when the oracle in the PRP experiment is e sub k, then B's simulation of A's expected environment is perfect from A's perspective, right? However, it's not anywhere near perfect when, in fact, B's oracle is random permutation, and in fact, we're counting on that. So because we have such different quality of simulation of the key recovery experiment, depending on whether or not the bit B is 1 or the bit B is 0, let's go ahead and condition on the value of B. This is a common trick. So we simply write out the probability that we're interested in, this PRP probability. We're trying to write this in terms of the key recovery advantage. We simply write this out as a conditional probability conditioning on the value of the bit B in the PRP experiment. And there would be a probability B equals 1 here and a probability B equals 0 here. But by definition, in the PRP experiment, that probability is half, so I just pulled it out. Now let's look at each of these in turn. These are the two cases we've been talking about. So, in the first case, when the bit b equals 1, what do we know? Well, given b equals 1, let's see, when does this event happen? The PRP experiment outputs 1 if and only if b's guess at the bit b is correct, which means if the bit b prime that b outputs is 1. Right? This outputs 1 if and only if b outputs 1 as well. Because specifically, the bit in the experiment is 1. Likewise, we know that b outputs 1 by construction of b. B outputs 1 if and only if this check passed in our code, right? That e under the key guess k prime of this fresh point z is in fact the output, equal to the output of the oracle. And because we're given, in this case, that b equals 1, we know the oracle is e sub k. Hence, b outputs 1 if and only if e k prime of z equals e k of z. Well, we know that happens for sure if k prime and k are the same, right? Because e is deterministic. So that's good, because that means whenever, in the case that the bit is 1, whenever a guesses the key correctly, we're going to output 1, which means the experiment outputs 1, which is what we want. Yeah? So it definitely happens when a guesses the correct key. But if you think about it for just a second, you realize that this check here, this could pass even if this key is not right. If it just so happens that for the value of z that we choose, we of course being b, and for that value, e agrees under this key and the one that was picked, we still output 1. So we're going to output 1 whenever a would guess the key, but we're also going to output 1, every so often when it doesn't guess the key either. So if we take this fact, combined with the fact that the simulation of A's expected key recovery experiment is perfect when the bit b equals 1, what can we conclude? We can conclude that the probability that this experiment outputs 1, given that the bit b is equal to 1, is equal to the probability that A wins the key recovery experiment. That's this, right? If A wins this perfectly simulated key recovery experiment by guessing the correct key, then B outputs 1 and the experiment outputs 1. So we know that at least this term is here. But also we said that this experiment could output 1 when the guess isn't correct, but it still passes this check that we've said. So the probability that this outputs 1 is the key recovery probability plus some probability over here that's at least, well, it's at least 0, of course, because it's probability. But the point is that there could be something here. We don't actually have to care what that something is. We just know that it's there. And because we have this inequality, what we can conclude is that, what have I done here? Oh, yeah, duh. I actually made a mistake when I was making this. This shouldn't be this way around. This should be, this inequality is pointing in the wrong direction, because it's not that we don't care that we care that it is this direction, right? The experiment outputs 1 with some probability when the key guess is wrong, but the check passes, right? So there's some potential for that over here. We don't actually have to analyze what that number is. We just know that the whole thing tells us that the chance that the PRP experiment outputs 1 for this constructed B, given that the bit was 1, is at least the probability that A guesses the key. And by definition, this is the key of recovery advantage of A. Right? So we can conclude that for this case. So we know that the key recovery advantage of A we can stick in right here. Follow that, let's go on to analyze then the slightly harder case. So what happens when we have B equal to 0, meaning that the oracle is a random permutation and not the block cipher? Well, we stop here. So given that b is equal to 0, it's just walking through what we did above here, this outputs 1 exactly when b correctly guesses that this bit is 0. So that means that when b's output is 0, this will output 1. But b's output is 0 when? Well, b outputs 1 when that check of the key k prime with the oracle passes, which means output 0 when it's not the case, right? At output 0 when the locally computed e sub k prime of z does not equal the output of the oracle, and given that the bit is 0, the oracle is a random permutation. So b outputs 0 in the case that the challenge bit is 0 means this outputs 1, if and only if this check doesn't pass. So we have to analyze what's the probability that this check doesn't pass. Well, this is where a little bit of comfort with probability helps. Let's think about this. We want to know what's the probability that this thing does not equal this thing for a new value of z. And this is where the new value of z part is going to come in super handy. Because look, if we fix any value, any n-bit string v, any of them. So I'm saying, like whatever value this takes, I don't really care. Fix any value of v, sorry. Then the probability that a random permutation on a point that's never been asked to it before equals this value z is at most this quantity here, I claim. Where does this come from? Well, let's think about the sort of lazy sampling perspective on filling in a random permutation. So if I draw here, the table for pi, right? In the experiment, this table is picked all at once at the beginning of the experiment. Well, hopefully by now you've convinced yourself at home that this lazy sampling approach to filling in a random permutation is exactly the same probabilistically as having picked pi all at once from the set of all permutations. So let's think about filling in this table, and this will help us see where this number comes from. Okay, so what's happened? If Q is the number of points that A asks, so I think I've said that anywhere yet, but just to remind you then that Q, when we actually write down the theorem statement, this is the number of A's queries, right? If A asks this many queries, then B also asks, well, it asks this many queries, plus it asks one at the end, but we know for sure that this many queries have been asked when B goes to make this check, right? So Q points have been asked. Well, think about now. These points, there were Q of them. I'm, just going to pretend like the top 3 were part of them, but you'll get the point. When the first point gets asked, how many values can you write in here? Well, of course, you can write in 2 to the n possible values. When the next one is asked, you have 2 to the n minus 1 possible values you can write in because this is a permutation, and so on. If you ask Q queries, then that means then that the total number of points that have been filled in so far is on the Qth query. So this was query 1. This was query 2, which means that on the Qth query, so maybe I'll draw in pretend like it was down here someplace. When the Qth query is asked, how many values can we write in here? Well, when the first query was asked, is this many. When the second query was asked, this many. So this is 2 to the n minus Q minus 1 possible choices for what to write in here. So that means that once Q values have been filled into the table, right? This was filling in Q values. Then B asks this next query to do the check, and it's on a fresh value of Z, which means that the probability that the random permutation, so maybe like here's the value Z, it's here, say. How many possible choices do we have for this? Well, it's obviously 2 to the n minus q. So the probability that the random permutation assigns to z any particular value v is at most this much. If v, the value that we're fixing here, if v is some value that's not yet in the table, then the probability is exactly this. If v is some value that's already in the table, remember I said you could fix any value v here. If this is some value that's already in the table, then of course this is 0, right? Because this is a new point, which means it can't be v because v was assigned to some previous thing. So that's why you get this less than or equal to, because it's either this or it's 0. But in any case, this statement is true. Well, since this is true for any value of v, what we really care about, of course, is the not equal, right? This is the equal. This is analyzing the probability that for any value of v, the random permutation on a first point hits it. But the test we really care about in this case, v is going to output 0, meaning it correctly guesses the bit, when this check doesn't pass, right? So the thing we actually care about is not the probability that pi of z equals v, but that pi of z not equals v. But of course, that's just 1 minus the probability that it did. So we can write this, it's 1 minus, and since we're upper bounding the term that we'd be subtracting, and when you upper bound something you subtract, that's the same as lower bounding the whole thing. So the probability that the random permutation pi on this new point z does not equal v, whatever v is at least this quantity. Which means in particular, if v is the value that this takes, then the chance that pi of z not equal this value is at least this, which is going to now let us stick something back into the expression above. So to remind you, we're going to stick that right here. Okay, so again, you might want to pause yourself and make sure you follow that whole line of argumentation, why it is that this is the correct value here. Assuming that you have, let's slide over to the next part of the argument. So, giving away the punchline too fast. So here we go. Let's conclude. We've done all the analysis. Now we just have to put it all back together. So remember, over to the left of this line, we conditioned this probability, the PRP advantage, the PRP probability, of b. We conditioned this on the value of the challenge bit, little b. And we've just analyzed that this probability is at least the key recovery advantage. This probability is at least 1 minus 1 over 2 to the n minus q. So that means this is going to turn into, a greater than or equal to. So that means then if we want to know about the actual advantage that b gets, we know we just have to multiply through this thing by 2 and subtract 1. That's exactly this by definition. So that's 2 times, and a big set of parentheses here, all of this stuff plugged in. It's 2 times a half times the key recovery advantage plus this other term, minus 1. Obviously, the 2 and the half cancel, so we end up with this plus 1, but the plus 1 and the minus 1 cancel, and we're left with this term at the end. And so we have that the PRP advantage is lower bounded by the key recovery advantage of A plus this extra additive term. Oops. Uh-oh, it just rotated. It might have rotated it slightly. So the conclusion from this and the previous analysis is exactly this statement. If I just rearrange slightly, right? If I take this term and throw it over on the other side, I get that the key recovery advantage of A is at most the PRP advantage of B plus this term here. So we need to stop and think about what exactly this is saying. Remember, our goal was to argue that PRP security implies key recovery security. Does this actually say that? Well, certainly if we didn't have this additive term here, then it would say that, right? Because PRP security means that there doesn't exist an efficient attacker that gets large value for advantage, which means that for every efficient attacker B, this has to be small, and if this is small and it's an upper bound, then that means this has to be small too. Hence, PRP security would imply key recovery security. And again, the direction of the inequality is given to you by remember the informal claim, was we have this sort of heavy arrow that points this direction that helps to tell you which direction this inequality goes. Well, that would be without this term. But we've got this additive term here, which means that the sort of the quality of this implication, there's a little bit of loss to it. Right? In the previous one that we did, there was no loss. It was just this thing equaled this thing. So the bound was as tight as you could possibly have it. Here we're saying, yeah, we have the implication, but there's some loss to it, right? And what's the loss? The loss is this term here. So we better hope that this is small. And indeed, this number here will be small so long as q doesn't approach 2 to the n. But that makes sense, right? If q approaches 2 to the n, then this thing becomes big, at which point you end up saying that the key recovery advantage is upper bounded by something that's like 1 or bigger than 1 even. So I guess actually not bigger than 1, as long as this thing is less than 2 to the n. But of course, that's a vacuous statement, right? To say that this thing is upper bounded by something that's close to 1, well, it's always upper bounded by 1. But the point is that this is telling you that if your key recovery attack doesn't ask, something like 2 to the n queries, this term is going to be small, right? So, imagine, for example, maybe write this on the side. So, for example, consider like n equals 128, and q equals, let's think of even a large number of queries, so like 2 to the 40. 2 to the 40. In fact, 2 to the 40, or even larger, could be like 2 to the 64. In fact, maybe that's even more interesting to kind of drive home the point. 2 to the 64 is a huge number, obviously. 2 to the 40 is already a big number. Exactly, I think it's like 20 million? I forget. In any case, let's say it's 2 to the 64. Well, so that in the bottom here, what do we have? We have 1 over 2 to the 128 minus 2 to the 64. And of course, this term here is completely negligible compared to this. In fact, even as this thing gets reasonably close, like 2 to the 100, which is, of course, a ridiculous number of queries to be able to ask. You're never going to be able to get away with that. This would still be a very, very small number. So that's good. You have this additive term here, but it's still a very, very small additive term. And so, in fact, the quality of the proof that we've given is good. This is actually a fairly tight bound. The PRP security of E tightly upper bounds the key recovery security. So what remains then, of course, is to analyze the resources that were used. And so the obvious one, of course, is the number of queries. Remember that B asks Q queries because every query that A asks, every query that A asks, B asks as well. And then there's one more at the end, right? And it checks the value of the key guess that's been given. About the time resources, well, I'm going to call this T plus a term, and with some abusive notation, a term that's like O of Q log Q. And this is, as I say, this is an abusive notation because Q is not an asymptotic term. But this is a pretty common abusive notation to see in cryptography. This simply means that we're hiding, some linear scaling here. This term here is strictly to account for the data structure needed to be able to store the queries and to be able to search for a point Z that's not in that set of queries. Of course, you can do it more efficiently than this, but you should be able to do it with at least this. So this is the running time, the time complexity, T prime of the B we constructed. And so given that, we can now write down the whole theorem. I told you that it's very often the case that the theorem itself, I didn't realize I had done that. The theorem itself, maybe I can hide that. No, it's not on that layer. I guess I just wrote it down. Bummer. Here, let me erase this. This is annoying. I didn't realize I was writing over top of this. You're wondering, how did he erase that and not erase this? Because it's on a different layer. Okay, so the actual theorem statement that we make. The theorem statement setup you could write before you actually started doing the proof. So fix a k and n that are at least 0 and let e, taking a k-bit key and having an n-bit block size, be a function family. Now, I've been talking about block ciphers, right? But in fact, this result's true for function families in general. You can talk about the PRP security of a function family, even a function family that doesn't give you permutations. They might not have very good PRP security because the function family itself is not a permutation. You can still talk about it. It's still a well-formed idea. So we can be a bit more general when we make this statement. Let's let E be a function family with this syntactic signature. Let A be a key recovery adversary for E. E recovery is hyphenated. Okay, so we're assuming the existence of some A. Then there exists a PRP adversary B that again is explicitly constructed in the proof of this theorem, because we're not just saying there's some existence proof here. This actually is a concrete result, such that this bound is true. And this is the thing that, you could have written up to here, and maybe even written down the advantage and had this inequality going in the right direction, but you wouldn't have known exactly what to write here until you were done. In any case, this is the bound that we prove, where Q is the number of oracle queries made by A. Moreover, let T be the time complexity of A, 2. Then B has time complexity, and I've just said it's T plus O of Q log Q, and V asks Q prime equals Q plus 1 queries. This is the security theorem statement that proves the thing that we wanted to prove, which was that PRP security implies key recovery security. So now you've seen this proof and another one in full. So I hope that by sort of following this recipe, these steps, you will be able to start thinking about how you would structure some of these kinds of proofs on your own, and you'll have a chance to do that coming up soon.